My quick announcement is that I'm expecting possibly an important phone call. It's one of those ones where they're going to call between a certain time, right? A certain time interval. And if I get this call during class, I'm going to take the call. I'm going to step outside and take it. And then probably, depending on where we are in the class, I'll have about 15 minutes left once I get that call, and then I'm going to have to leave for about 30 minutes. Okay? So if this happens like in the next 15 minutes, we're going to have the full class, and what I have is a sample of a past semester's midterm that I'm going to hand out, and I'm going to let you all sit and work in groups. And then I'll come back, and you'll still be here, and then we'll talk about it. Okay? Yes? But I'm not going to cancel class. All right, we good? Just real quick about the bonus, because I was talking about it. Some of you turned in. I have not even looked at the bonus. If you emailed me, I haven't even opened those yet. But the most interesting thing was what was happening when x was 0. And when x is 0, you're on the y-axis. And this is a picture of that function. That's a picture of it. And if you look along the y-axis, you can see that along this, there appears to be like this ridge. Do you all see that? And so when you try and compute capital D when x is 0, I think you get 0. And that's inconclusive. So I just wanted to see if anyone would investigate it a little further. Because, I mean, if those are like little ridges, right? Like if you take a piece of paper and fold it over, I mean, every point along there would be a maximum, wouldn't it? Local, maybe? So anyway, but you have to really kind of get deep into some other things like hold y equal to a constant, and then just investigate the behavior on both sides. And people either did it or didn't. And I'm not going to take off if you didn't. I just want to see how people would handle it.
But what if you're looking at the x-axis?
When y is 0?
Yeah.
That was a little different along the y-axis. Let me see. Along the y-axis, I'm sorry, when x is 0 or when y is 0?
When y is 0.
When y is 0, you're right in here, and you don't have a maximum. But I don't think D was 0 when y was 0.
Okay. Yeah, I don't remember. I gotta look.
All right. Let's get into today's material. So if you remember from the beginning of last class, we talked about we're trying to find the maximum and minimum values of these functions. And in the first part of this lecture for this section, we did not have any restriction on the domain. And I said that was just like in Cal 1 when we're looking at some function and we're just trying to find local maximums and local minimums. Now what we're going to do is we're going to move into something that is more in line with this situation from Cal 1, which is where we cut or restricted the domain of the function. And when we restrict the domain, right, on a closed interval here, then it will have what we called an absolute maximum and an absolute minimum. There will be a highest and lowest point on the graph if this is a continuous function on a closed interval, right? Okay, so that's where we're going here. But the first natural question is, if you're in Cal 1 and you want to start and stop here, we call it A and B. AB is a closed interval, which means it's all the numbers in between, right? You can plug those into the function, and you can plug the endpoints in, right? We call this a closed interval. If our domain for our functions live in R2, right, then what is a closed interval in R2? Well, we don't call it a closed interval. We call it a closed set. So we have to start, before we get into this, understanding what we mean by closed and bounded sets. So there's some pictures here. A circle is an example of a closed set. This is a closed set. These are not closed. So do you see the little dashes around the edges? That would mean you don't include the boundaries. So like on this one, you don't include any of the boundary. Here you include all of the boundary except one point. That's not closed. Here you include one boundary, but you don't include these. This is not closed. You have to have all boundary points included for it to be a closed set. To be a bounded set is a little more complicated, but the idea is that your set must be finite. So imagine that I have a set here. Okay? This lives in two-dimensional space. We could orient the x and y axes somewhere, x and y. That's a closed set, right? If I include all these and I tell you the boundaries included, that's a closed set. To figure out if it's bounded, we just need to be able to draw a circle around it. If we can draw a circle around it and include everything, then it's bounded. If it's impossible to draw a circle around it, then it's going to be unbounded. So one example of a set that's unbounded would be, let's say, the y-axis and everything out this way. Okay? That's an unbounded set. So our theorems that we have here for this part of this section require that we're looking at a function on a closed bounded set. Then everything that we talk about is okay. If you go outside of that and you start talking about, unbounded, or you start talking about where the boundary is not included, then you have some bigger issues. In fact, y'all know who the Unabomber is? Ted Kaczynski? No? It's been that long? Y'all know who the Unabomber is?
Yeah.
You heard of him before?
Nailed,
He was a mathematician, actually. He was pretty bright mathematician. I forget where he went to school. And then he's decided to just become a hermit and then try and kill people by sending them bombs in the mail. And he was successful for many, many years. And finally they found him in some shed somewhere, and they arrested him, and he's in jail now. But one of the things that he studied when he was in his mathematics was what are called boundary value problems, which are where you're starting to investigate the way functions behave along these boundaries when the boundaries aren't included, or functions can start acting crazy there sometimes. So we study them at a higher level. But here we're going to include the boundaries and we're going to be happy. That's a little random tidbit of information for you. Useless information. Kind of like the number of ridges on a dime. So one could look at this several ways. One could say, wow, that's interesting. The Unabomber was a mathematician. Or you could also look at it as mathematics makes you crazy and makes you want to go hurt people. Different perspectives. All right, so what does this new extreme value theorem for functions of two variables say? It says, I know this is hard to read, but this is in the book, okay? If f is a continuous function, all right, so it has to be nice and smooth. We don't have any crazy things happening. On a closed bounded set, capital D. So we have a closed bounded set that is its domain. It's restricted to that. Then f attains an absolute maximum value and an absolute minimum value at some points inside of D. That means it has to find a absolute max and an absolute min somewhere on that domain. It might be, let's just do a simple D, okay, capital D. This is the domain. Closed bounded set, right? The graph of f is above this, right? We turn it over, and it's what we've been looking at before. And somewhere in here, there's some point in here that when I plug it in, I get a maximum, the maximum I'm going to get. And somewhere in here, I'm going to get a minimum. I'm guaranteed both. It might be that the point's in here. It might be that the point's on the boundary. All this theorem says is that we're guaranteed the existence of it. All right? To find the absolute maximum, to actually find it, here's what we do. We find the values of f at the critical points of f in D. So what we're going to do first, okay, first step, is to act like this is not a closed bounded set and do exactly what we did last class. That identifies local maximums and minimums, doesn't it? Then what we do is we find the extreme values of f on the boundary. And this is the big difference. What we're going to do is we're going to say, it's kind of like, again, from Cal 1. we can set the first derivative equal to 0 to find these points, right? From Cal 1? But that tells us nothing about these. So what we need to do is evaluate the function at the endpoints, right? That's what this step is saying. We need to somehow evaluate the function, not at the endpoints, because we don't have endpoints, we have boundary, right? We need to evaluate the function on the boundary and figure out where it's the highest and lowest. That's going to be a little bit troublesome to do that. Then what we do is we compare our answers from here and here. The largest that we get is our max. The smallest that we get is our min. And that's the procedure. All right? Does that kind of make sense? You all have like glared looks on your face. Spring break is not next week. It's the week after. Then you can go ahead and check out for a while. All right, so let's see if we can handle this. We have a function given to us, f of x equals 3 plus xy minus x minus 2y. We want to find the absolute max and minimum values of this function on the closed triangle with these vertices. Okay, so first let's just take a look at this function. This is the function if I do not restrict its domain. Right, there it is. But I only want to look at the domain restricted, let's see, at the point 1, 0, that's here. The point 5, 0, that's here. And the point 1, 4, here. So those are the vertices of a triangle. And I'm going to treat that as a closed bounded set. And just imagine just taking these points and plugging them into the function and throwing everything else out the window. All right? And just looking at that. What's the highest and lowest value of the function on that closed set? Can you all kind of visualize that or not? Yeah? There's the triangle. Okay? That's the two-dimensional triangle that I just drew. That's your domain. This right here, let's see if I can do this. Make that a little bigger. This right here is the domain laying on the ground in three-dimensional space. Do y'all see that? Don't ask me why it's cut off. That there's something wrong with the code. I need to plot more points. But okay, are y'all okay with the fact that that's that domain laying on the ground? Okay, here's the surface. If I don't restrict the domain, there's the surface. Okay, there it is. Now, if I restrict the domain, can you all see the part we're talking about there? I'm going to pull the surface with an unrestricted domain out. It's a little easier to see. Hopefully, you can see that. And I'm going to pull it out completely. And then the green is the surface restricted to that triangle. Do you all see that? And if I look at it from the top, it should lay right on top of it, right? Do you all notice some parts of the surface go above our domain and some below? Okay, so the points we're interested in, here we go. The points we're interested in are these points. Yeah, that looks like where we're having absolute max and min, right? And we're going to have to go in and figure it out. Okay, y'all okay with this? So let's talk about, take these points out for a second. Let's talk about if we were just to take, on this triangle, if we just took this line right here, just this line, and plug just that line into the function, what would it draw? Would it be a surface? Would it be a vector? What would it be? If just this line gets plugged into the function, what comes out up there? A curve, right? So I should have, let me make sure I get my lines right here. There's that line. Okay, so there it is in the domain. Do you see the line in the domain right here? If you take each one of these points and plug them in, right? This blue line represents the edge of the surface, that curve, right? Do y'all follow that? Okay. So if I look at just this right here, if I say, hey, let's just focus all our attention on just these points, it really just draws a line, doesn't it? And I can find the highest and lowest points on a line, can't I? Sure, I should be able to. Now, I could do the same thing for each of the boundaries. I could go to L2, which is this black line right here. And imagine plugging just those into the function, and you would get this edge. Now, let me just spin it around so you can see it. Uh-oh, I'm losing it. There it is. Okay, so I had to turn it on the back side to see it. But if you take just this edge and plug it in, some of them go up, some of them go down, right? What shape does this look like? Parabola. Can you find the maximum of a parabola? Absolutely. From Cal 1, you should be able to, right? And then if I take this last line along the triangle, this red one, I have to spin it back this way, look at it this way, then there's the red line, plug those in, you get another line, don't you? And we should be able to find the maximum of a line. That's the way we're going to deal with these. We are trying to look where the function has its maximum here. We're going to look along the boundary, which is going to turn into, in this case, 3 separate problems that we have to do. And then we're going to have to look at the interior, all the stuff inside. But to do the inside, we do what we did last class. Because when we look on the inside, what we do is we forget the outside. We forget the boundary. We just say, look everywhere and find me the local max and mins. Got it? Questions? All right. That's just proving that those points lie somewhere. So check this out. It looks like our minimums are occurring at these vertices, aren't they? Looks like it. But the maximum, this maximum here, looks like it occurs somewhere along this boundary, right? And then the other maximum look like the same height. I can't tell just from the picture. We'll have to work it out and do the math. But that one looks like it's happening at a vertice, like right here at the origin. So I wonder, do the maximums and minimums always, absolute maximums and minimums always occur on the boundary? No. Okay, they don't. But you have to check the boundary. In this particular problem, it looks like they're all going to be on the boundary. All right, you ready to go after this? All right, good. I'm glad. So where do we begin? All right, so where do we begin? Well, let's look at the critical numbers, the things that make the partials 0. Why are those important to us? The numbers that make the partials 0 is where we would have any local maximums and minimums, right? So I'm going to find, first of all, the critical numbers. Critical points. Let's call them critical points, not numbers. And so I'm going to set the partials equal to 0. Partial with respect to x is what? Y minus 1 equals 0. And then the partial with respect to y is x minus 2 equals 0. And that's nice, isn't it? X and y are pretty easy to solve for here. 2, 1. It's a lot like the bonus problem was, setting those partials equal to 0, right? Now, what did we do last class at this point? Once we found where this partial was 0, where these partials were 0. What did we do last class?
Evaluated D.
We figured out what D was, right? Capital D? Now, here's the thing. We actually don't need to do that in this. Here's why. If you go back to Cal 1, remember what we did in Cal 1. We found where the derivative was 0, didn't we? And then all we did is we found where it was 0. We took the endpoints. We plugged all of those into the original function and compared, right? Same thing here. I know that this point might be important, but it's the only one that might be important on the entire domain. So there's no need for D. Understand that? There's no need. We're just going to keep that point. Later on, we're going to plug it into this function, and we'll compare it to what's happening on the boundaries. If this turns out to give us a higher value than everything else, it'll be our absolute max. If it doesn't, then, well, at least we looked, right? This is allowing us to look inside. Oh, wait, hold on. We have to make sure this point lives in our domain. Forgot to look. Hold on. We didn't look at that. Let's sketch the domain even though I had it. 1, 5, 4. We had our triangle here. Does this critical point live in there? Does it live in here? Yeah, it's 2,